Well, hello everybody. Welcome to MP3672. These are going to be a series of videos which are going to try and support a little bit more about the functions of each type of aspect that you'll find in specific softwares that we'll be using. So if you're worried that you've never seen MATLAB before and you're thinking, I'm not the most confident, don't worry. These are going to be there to support you, to prompt questions that you may have. These are also going to be supported with some live webinar sessions that we'll do. They won't be as frequent as the classes, but we'll be doing that as well to try and get you up to speed and plenty of confidence. In semester 1 we're going to focus purely on the use of ANSYS. We're going to be using it to solve static problems. We're going to also be using it to solve some level of dynamic problems. So if you've not done already, make sure that you have ANSYS installed on the PC and open it up. Now I've opened up Workbench. When you open up Workbench, this is what it introduces. So down the left side you've got your analysis types. You've got all sorts going on. So let's just take a quick look through what it can offer. I don't know who's used this before, but if you've used this before you'll know that it's quite a vast different sets of options. If you want to really go into depths about getting real sets of results that are a little bit more statistically comparable, you can use the Six Sigma analysis tools. For those of you who may have done design of experiments before, this will allow you to do things such as the response surface, all different types. My typical one personally that I've always used is the response surface, purely because I can quantify exactly how much I've done, and it makes it just that little bit sharper. So this is the design exploration area. The custom systems, I'll leave you to have a little play around with this, because this allows you to bring in templates and then remodel them around your recommendations and what you need. The composite systems, the component systems, we are going to be touching a little bit of mechanical APDL. Now, mechanical APDL has notoriously left people feeling a little bit awkward, and they're not the most confident with that. The best way to describe this is if you're doing quite in-depth research and you're looking at material composition and you're looking at material displacements or fracturing, mechanical APDL will allow you to write macros in the background that run alongside of your simulation. So if there's a specific type of behavior that occurs, it allows you to have that. So for example, let's say you're going to simulate a simple layup of, I don't know, six layers of carbon fiber, but then let's say you've got certain sizes of grains, or let's say pieces of just grains of sand that are emerging, and whoever laid it up, it wasn't quite right, and you want to actually look at that type. What you can actually do is you can use one of the functions in it, which is a Monte Carlo theory function, which sounds really sophisticated. All it means is it's a random number generator. You can then apply that to a specific size of grain. This then will randomly emerge all the way through what you're laying up, and it will allow you to look at what could plausibly happen if somebody was to drop sand into it, and you can look at how it would fail. I mean, we know that it's not the best thing to do, but it's this type of thing that you can do. I'm just going to drop this down again. Right, these sets here is where we are going to focus. Now I should point out, ANSYS is absolutely huge. It can do all sorts. What, with the freedom of the webinars, I mean with the freedom of these videos, sorry, what we can do is perhaps work through some of these tools. In class, our focus will be on structural static and also explicit dynamics. what we're going to be doing as we're working through, we're going to be looking at mesh, and we're going to be looking at how mesh is the overall controller of everything that you do, the visual representation of the geometry that you do. When we get to explicit dynamics, we'll go on to the latest type of technologies in the mesh, which is what is nicknamed the corrosive mesh. Basically, mesh can have a Young's modulus defined between two nodes, and when it's extended, if it's extended enough, imagine there is a spring in between these two nodes. If it's extended enough, the spring will snap, and what you can actually end up with is debris. You can end up with pieces breaking off something. But I know that's rushing heavily ahead, so let's just start by just having a little bit of a play around with what we got. So to keep things nice and simple for the start, what I'm going to do is I'm going to left click on static structural, drag, and with my finger on the left mouse button, as I drag it over, you'll see that it gives you a green center boxing. Now this is just purely to say, right, I can be dropped into here. Once you're into the target area, release your finger from the left mouse button, and then 3, 2, 1. Right, so this is our first simulation set. What this will do is it will take a template. It will take a template of things that it needs to know to successfully run. Whilst we're working through, we are going to drop in bits of theory to support what it is that you're looking at. Because somebody once told me that the best thing to be able to do with softwares is to know what your limits are, and then you know what you can really push this to do, and what you can make it do. But if you think it will do everything and solve everything, it won't, because if you put crap in, you will get crap out as the simulation goes. On your engineering data, right, so let's have a little bit of a explore as to what this is talking about. Engineering data. If I right click and then I go to edit, now let me just drag this over. On the university systems, sometimes this does not appear this way. It can be frustrating and it can feel like something's gone horribly wrong. So let's I'm just going to show you how to reset that. So I'll go view, and you see there where you've got reset window layout or reset workspace layout. Go workspace layout, and this will look like this. It can be frustrating, and I don't really know why it's happening, but it is happening. So what do we know? In here, you know, when I first started using this software, I kind of looked and thought, this is well poor. All I've actually got here is just steel. That is so crap. Now, it's my total misunderstanding with that. First things first, as you can imagine, all the material data set. Now this is a stereotype. This is an off-the-shelf value. Should notice you've got your description. If you chase back this source, it will tell you exactly who did the original testing for this as well. If you have your own data sets, in fact, let me just bring this over, because there's so much to see here, it's crazy. So cycling, this is its fatigue life. This is the cycling logarithmically, how it will perform under certain conditions based on the mean stress. But if we go on stress parameters, what you can see there is the breakdown of each component. You can see how well the not component, I suppose you could refer it to as a component, but you can see how well it will perform under certain states. This in essence is like a miniature method of material selection. Make sure that it meets the requirement that you're looking for, because if you look at your reverse failures up to 2 newtons logarithmically, you can see where your overlap lies. So you can see there that between your plastic strain life and your elastic strain life, around 4.5 newtons, you're going to get some sort of behavior that's going on. Oh yeah, that's to the power of 10, just realized. but that's where you'll get this overlap, and then you'll get some sort of interface between it, and you may look at some bending. Right, so this is what is presently in the simulation. Like SolidWorks, when you first open up the software, it will not put everything in there because it's trying to keep everything as efficient as possible. So when it loads, it's not loading loads and loads of data. As if it's loading loads and loads of data, you can be waiting for it to open. So now, if I want to change, if I want to introduce more materials, let's go to Engineering Data Sources. I go on there. What we've got now is everything that the system can offer. Now, I should point out there is a lot of extra things on here that I added into it. So I have some graphene models on here. I have a few extra bits on here. So I'm just going to squeeze that up there. Right. So if I go General Materials, this is quite good. If I bring this up, this is what ANSYS has saved in its databases. Now I know a lot will look and go, well, that's a bit crap, is it not anymore? Is it not any more specific? Well, when we're going through the classes, I'm going to show you how to bring in more exotic materials. If there's a specific aluminium that you need, it's not impossible to get it, but I want to leave a little bit of joy for the classes as well. So we're not going to cover that in these. This is going to be more of just familiarizing ourselves with softwares. So if you look here, we have aluminium alloy. But if you look at structural steel, you see a book there. That book says that it's being used in the present simulation because it's been added to our project. I'm going to add an aluminium alloy. I'm going to left click on the plus symbol to add it to the project that we're doing. And then let's just bring that back down. Now that's all I want to do at this point. You do look, you've got thermal materials, fluid materials, composites. I think in the one that you've got, you will see composite materials, and you'll also see geomechanical materials. But what I'm going to do now is left click on my data sources to turn it off. And what you see here now is we've got a new material that's added in. So I can now work with this, which is great. This is where you'll have to get really comfortable with clicking the X to actually close something. See here we're on the engineering data. I'm going to left click to close it. When you're saving, save inside of this workspace. It's only here where all the saving happens. Make sure you do that, and make sure you do that religiously, just to make sure that you've always got something there that you've always been keeping up to date. So all we're going to do, we're going to do the basic. We're going to take a basic bar and let's just bend it. It's a basic thing to do, and it allows you to just get a bit more confident and a bit more clear about how this thing functions. So in geometry, now I can import from a CAD system, which as we progress a little bit, what we'll do is do that, because modeling in these systems, I know a lot of staff are very happy to model in these systems. I found them a bit clunky, but that's only a personal experience, and I prefer to use SolidWorks, and then I can export straight from there. What I'll do is go to new design modeler geometry. You can use Space Claim if you're happy with it, but I would say just use New Design Modeler if you're new to this. So I'm going to left click. And just realize it's opened up outside of your viewing window. So when it opens, this is what you will get. If you get something that comes up and asks you for units, make sure you click millimeters. And right, so let's do a bar. Let's go 60 millimeters of diameter, so it's quite a hefty bar. And then we'll put it out at 550, 600 millimeters in length. So I'm going to go, you'll see here on this modeler I can choose plane locations. Here's the typical datum. What I want to do is I'm going to model the bar along what would be the Z-axis. So that is going to be where my extension will lie. So left clicking once onto the XY plane. You see where modeling is? Go to the left, you've got sketching. And I'm going to go circle. Bring it back over. Now this is just where you've got to get used to doing this in this modeler. You'll see why I prefer SolidWorks. You'll notice the pencil comes in. If I bring it across, you'll notice that the line itself is highlighting, and I've got what is like a marker appearing, similar to what you get in SolidWorks. Now what I want to do is I want it to locate itself to the middle. So you'll notice there it looks to have been, it's more of rectangular squares. Well, let's call it a square. Left click onto that. Now I've left clicked, just tapping left click. So I've let go of left click now. It's just so you're clear, because it can be a little bit confusing, because often we all get used to keeping his finger on left click and then letting go for it to be centered. This is left click to start it, left click to finish it. And another thing, another pet hate, I'm not selling this model very well at all. Another pet hate is normally we can put this in and then we'll get a full layout of its diameter and everything, and with this we don't get anything. It doesn't give us anything. What we've now got to do is go to dimensions. See how we got general? Left click onto general, and I'm just gonna left click once. Did the same thing, I opened it up, left clicked once. You'll notice now that once we've put that dimension on, it comes in as D1 on the front. Now you can change this, so if you go on to dimensions, go to the bottom where it says display. If I left click on there, you'll see it's got name or value. Now if you're, well, personally I like to see the value. So if I click on value, I could drop the name if I wish and it would just give me the diameter. If you have lots and lots of dimensions, it can be useful to put the diameter on the name as well. But you'll notice here I'm actually in meters, so this needs to be a bit smaller than that. Now what we agreed was 60 millimeters. So yeah, another thing I've just quickly jumped over. I like to be able to click on the dimension in the working space. In this system you cannot. So this is why over on the left here, this is why I've clicked into there, because I'm unable to do anything else. So I'm going to go 60 millimeters. You go 60 millimeters. So units in this case in ANSYS don't work. It tries to remain unitless as much as possible. This is just put on here just for a recording to give you an idea of size and so forth, but it does try to remain as much as possible. So I'll go 60 over 1000. That didn't work either. So sadly in this case I've never found any shortcuts ever in ANSYS. It does insist on certain things. So what I actually want is 60 millimeters, and because I'm in meters, if you already chose millimeters when you started this, you won't have this problem. Hence why I said make sure you choose. So I'll go 0.06, and that is correct. And if you look here, it's now vanished because it's so small. I'm going to right click, down my options I've got zoom to fit, and this is a useful tool also. right click, keep your finger on the right click, and this is the automatic zoom to space. Right, so we've now got our geometry here. It's still not complete because we want to do an extrusion. This is going to be our, I think it was a 550 millimeters. So I come back to modeling. This now becomes confirmed. I'm going to go to extrude. Now what it says is you click onto extrude and it says, okay, what you're extruding, give me a geometry. So I can either click on here or I can click on the sketch, which is inside of my XY plane. So I'll click on the area here and then apply. Right. The next thing it says is operation. Are we adding material? Are we freezing material? We will cover frozen materials and why, but for this case we're just adding material. Directional vector. As like in SolidWorks, CATIA, Inventor, any type of CAD system, it always needs to know the direction in which it's traveling. So you can manipulate that direction if you wish. In this case we're just gonna stay into the normal based on the XY plane. So it knows that it's moving in a normal direction based on the XY plane. Just to reiterate, normal to a plane means that it is perpendicular to its flat state. The next direction, as you can imagine, we have reverse, we have symmetrical, we have isosymmetrical. What we're going to stay with is just a normal, and then extent, fixed. You see there it's at 1 meter. Now I need this to be 550, so this becomes 0.550. Well, 0.55 should be more like it. And then we get to here, as it says, as thin surface. I can turn this into just a surface if I wished. The benefit of doing this is if I turn it into a surface, it allows me to put in really exotic data, such as anything from Kevlar to carbon fiber, but there is lots of issues with that, and we will cover that more and more that we go through this. This is just more of an introduction as to just getting to know what we're doing. Right, so I'm going to go zoom to fit, and then I'm going to go generate, because you'll notice now, in fact, if I come back down here, we should be able to see. You can see that is the length of the bar, but it's a simulated version. Once it's done that, it's kind of like in the SolidWorks system, you know, when you choose the length of what you're doing, you choose the parameters of what you're interested in. Is it tapered? Is it not? Directions that you're going, and then you hit the green tick. In essence, when you confirm that, what you're looking to do is then say, this is happy what I'm with, I'm now going to generate based on these parameters that I've put in. So here we've got generate, so I generate, and then let me go zoom to fit, and if you've done it right, that is what you should end up with. This is a 60mm in 60mm diameter by 550mm bar, and at this point, well, at this point it's made of steel, but we can have a multiple option. So if you're happy with that and it looks right, if you've made any mistakes and you've gone through, what I would recommend is that you go back to your sketch and just make sure everything's correct there, and then go to your extrusion and just run this section a little bit again, just to get happy with the process of doing this. Well, another thing I wanted to point out is once it's been generated, you'll notice here it says one part, one body. Then we have solid. Great bit of kit. Gives us volume of what it is, surface area, tells us it's a solid. We can even manipulate this. We can change, we can play around with this. We can do all sorts to this. But this is our system here. So we're happy with that. This is the weird bit. What we're going to do is close design modeler. Now, everybody I've ever taught this to kind of go, what do you mean close it? Are we not going to wreck something? Is it not going to get broken? Don't forget what I said at the start. I close the design modeler and save it here. It's always in the workspace. Make sure you save it here. And I do need to stress, when you save it, what it will do is it will save, and it will save model files, calculation files, meshing files. So often to do these type of things, it's quite good to put them into a singularized folder, because when they're in a singularized folder, it just means that you can move them. If you can't, it can be very problematic from the start. So let's move on to the good stuff. Let's go to model. No, let's not go model. Let's go setup. Because what this is saying here is, okay, you give me engineering data, I can work with that. And then it's going, okay, I've got geometry. Model's saying, I've got this floating in space, I need parameters to be changed for this to be confirmed. In model, setup, solution and results, we are now going to move into the template workspace area. So I'm going to right click on setup and I'm going to go edit. Give it a minute. As it's coming in, you'll see a little bar just to confirm that it's bringing the model in. This took about a second. If you have very complicated geometry, this can take 5 minutes sometimes. It just depends what it is that you're doing. So let's have a bit of a wander around what we got. Let me just close that, as I'm going to get emails left, right and centre. So we've got model A4. This is the model template. So you open the model template, and I'm just going to extend the child from the geometry, and then you have a singularized solid. In this case, it's only a single part, but if you end up with a large assembly, you can end up with 30, 40 different things that are going on. Let's have a little bit of a wander around what this is. At the minute, there's nothing on it, so it's the statistics are kept low at 0 because we've not done anything to it yet. The properties, we have the centroids, we have the moments of inertia of the actual thing. We can let me just bring that back. We have the boundary box. Within the boundary box, it will give us, imagine that there is a box around it. The box around it is measured at this area, so this would be the pocket in which the component sits in. Thermal strain effects, we've got that turned on. Non-linear effects, we've got that turned on. The type of assessment, going the type of material, sorry, at this point is set to the default of structural steel. But as I was saying earlier, we introduced the aluminium, so let's turn it to aluminium. Let's see what happens. So I'm going to left click, and as I go to the arrow, I can either go to an import, I can go to bring in more stuff, or where I've got the aluminium alloy, left click. Now the material is represented in that form, which is great. So let me just close these. Get to behavior. In this case, we're going to leave behavior as a none. We don't need to actually play around with that just yet. The reference template. Reference template will refer to its centroid mass. Now, if we go by environment, we're essentially saying that we're more considering how this thing is going to dynamically affect around its rest of it. But because we have a bar, we're not too fussed. We can stay by environment because we're going to fix one end, and we are basically going to hit it. We're going to hang, I don't know, let's go something daft. Let's go 800 newtons. We're going to hang 800 newtons straight off the bar and look at the effects of what it causes. Right, and flexible. In this case, we can have flexible, rigid, or gasket. In this case, the flexible side implies that this thing will be considered. If we make it rigid, what we could do is we could take something and hit this bar, and this bar wouldn't move, and we could just look at the effect of what was being hit, if you know what I mean. So if we had like another bar to hit it, but we made this bar rigid, we made the other bar flexible, when the two came into collision, what would happen is the central bar would stay rigid. It wouldn't register a lot to the effect, but it would all be passed purely to our target impact bar. So we can centralize a real dramatic effect of what's occurring. You'd still get force transfer, but it would be all centered more around the deformation of the main bar that we would be targeting. In our case, we're going to leave this flexible because we've only got one target in here. The coordinate system. Now, if you look at the coordinate system here, you'll notice it's come from how it's been modeled. We can add more. So if I go to my coordinate system, I can insert a new coordinate system. This will allow me to really dramatically affect things. I can say this area here is being hit by a certain force. I don't even need the geometry. I could just say it's basically on the coordinate system, or I can have the geometry to hit it. This is where you can do all sorts. Close this and close this. Right, let's get to the mesh. As I said before, we are going to really go through this quite a bit. But the meshing, best way to see this is it's like a spider's web. If you imagine a spider's web and how it deforms when if you push your finger onto it, it will stretch. 1 second. Now this may sound really daft, but I've just found this GIF, whatever the hell you call it. But when you look at the spider's web, see how it's deforming? It deforms almost linear-like. The mesh, when we go into a lot more theory about this, the mesh performs exactly the same way. What it will do is, if you consider these points here to here, how it elasticates almost linear-like. It's not non-linear. These things will deform almost in 2 points, almost like a coordinates base. Now, I show this because it sounds daft, but a lot of theory is based around how these things will deform, how these things will structurally move. As we go through, I want to discuss more about nodes. I want to talk more about nodes. In class, we're going to have a lot of discussion about nodes and how they function. So, what we're going to do is wrap this in what would be a spider's web. So, normally when I run these simulations, I don't try to do the most sophisticated thing in the world straight away. I get the basic bog standard, quite poor shitty thing running, and then I'll refine and refine and refine. Just because personally I'm never that confident to go, yep, I am that amazing, look at what I've done. So when it comes to the mesh, you'll notice that there is a lightning bolt. This is essentially saying I do have something I can use. It's a basic one. So what I'll do, I've right clicked on mesh and I'm going to go generate mesh. Now this is the typical type of thing. Now this is something really amazing that ANSYS is quite renowned for. You see how we have typical shapes here, but you've actually got 6-sided points on it as well. A lot of systems, a lot of smaller systems for FEA do not have this ability. They're unable to have multiple node reflections all the way through. What you end up with is just triangles. What you end up with is, well, your tetrahedral as it should be. I'm just going to try and find you an example. Let me just find one. Oh, this is a great example. 2 seconds. Let me bring this across. See here how everything there is all in triangles. This is purely because it's only got access to tetrahedral meshing procedures. ANSYS and some of the bigger end FEA systems have the ability to be able to multi-mesh methods. We are going to look more in depth about this, and we are going to look at how this behaves. But the basic function of this is, between each node there is what will be a spider's web thread. Each spider's web thread has a representation. The representation would be our Young's modulus. The node, as the node moves, because we have a Young's modulus, because we have a displacement, we have original length, we have a changing length, or the original length, which will give us our strain. We have our Young's modulus, and Young's modulus is equal to stress over strain. So we have the basic foundation, the basic fundamentals of what we need to know. So we know the displacement, we know the stress, we know the strain. The issue is when you look at these meshing procedures, what if there is a failure that occurs around this area? If it can only take into consideration here and here, there's possible areas of windows where it could go wrong. This is absolutely correct. And these are some of the biggest problems with FEA that you will find. The thing that you've always got to keep in mind is these softwares are only accurate to a certain degree. As we go through this and we drop in more and more sophisticated meshes, you should really start to see as to why they are. So, let's go. Let's get this running. So I'm going to go solution. No, I'm going to go static structural, sorry. Notice now we're back to the normal type. Two ways you can do it. You've got the environment up here, or if I go to static structural, I'm going to right click, I'm going to go insert. Everything is here. All we're going to do is we're going to hang, I think we said 800 newtons. May have said 600. Forgotten. Should have written that down. I'm going to go fixed support. Now this will imply that this thing is fixed. It's not got any sort of behavior where it can just slip away or anything like that. This thing is not moving for dear life. This thing is fixed. I'm going to left click on this face. You'll notice it's green. This is only just to say, okay, it's selected, and with the fixed geometry, fixed support, it now says geometry. If I click apply, what it'll do is go, now I think that is more like a purple. Some students have told me it's blue. I think that's purple. Massive tangent, I know, but I think that's purple. Anyway, so once it's purple, you now know it's locked in. It's happy. Now I'll show you the biggest thing that happens a lot. When you're in class, you're rushing through this, and it can be a little bit intimidating. You kind of go, quick, 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 gotta get it working, gotta be just as good as everybody else. I'll show you what happens. So if I go back again, go static structural, and go right click, and then go insert. Now what we're going to do, I think we just hang a force off it. That's what we'd agreed, a force. So I'm going to go to force. This is the biggest mistake. I'm going to click geometry. That is the biggest mistake that happens to at least one person. If it does happen, don't feel bad. You're not the first, and you're definitely not the last for this to happen to. Now the reason it's such a mistake is I just added a force where it's fixed. So when I run this simulation, it's going to come back and go, this is really good because nothing happened. Because it's put a force on a fixed place. You're trying to get an unstoppable force to get to move an unmovable object. It's just an ultimate cancellation. So doing that is wrong. What I'm going to do, flip it round to the other side. Left click here. If I click right, you'll notice it's now gone. Now I'm going to go apply. And I'm going to go in the Y. I actually wanted to move in the Y component. I can go vector. If I go vector, and let's just say I got 800, so I'll go 800 newtons. Vectors are normal to the face that you've selected. Notice here you've got an arrow out. I can change direction, but only in specific points. So they're good for some things, pain in the arse for others. I don't want to do that. I'm going to go component. So you see where we got vector, got the arrow down. I'm going to go down to the arrow. Going to go components, and where we've got Y, on the Y component, I'm going to go. Now this is something else as well. A lot of SolidWorks systems, things like that, or Inventor, things like that, they often allow you to choose which way it's going. This is a singularized input. Also as well, look at the coordinate system. The coordinate system we were talking about. So what I'm going to do, because I want this to move downwards in opposed to the datum, I'm going to minus 800. If I go, okay, and what we see, if we just zoom that area in, we've got the arrow moving downwards, and let me just bring that round. I'm going to right click it. This is right click and then drag a bar over, by the way. It's a really useful tool. I love it. Love it. Right, so that's what we got. Now, I'm going to go to solution, and I'm going to go deformation. Let's look at a total deformation. There is a lot more to this, but let's just look at total deformation. Let's look at maximum stress. And then I'm going to go strain, just for they're obviously going to be comparable because it's stress and strain. And then once we're happy with what we got, in fact, no, what I'll do, because this might be quite cool, I'm going to just delete that off. So I'm going to go solve. We hit solve, it runs through the calculation, it runs through the deformation of the mesh, which we need to go through a lot more. I find it difficult to actually draw the mesh on the screen, but I'll find a solution. So if I go equivalent stress, so what we got now is what you'd imagine. I can animate that. So this is the bar being deforming. As you'd imagine, the actual main concentration of stress is coming to this area here, not at the actual peak. So the peak's held, then it's totally held here. The elastic deformation comes heaviest here when the true largest area of deflection is actually on the end, because don't forget that's where we were hanging the weight. So when you look now, what you've got is you've got maximum above, maximum beneath. There's a lot more to do with this, a lot more, but I wanted you just to get a little bit happier with that. Now, let's say I'd forgotten to add my strain. If I'm running a simulation, it can take a long time for these things to calculate. This was quick because it's just a bar. But if I go solution, if I go solution, and then let's say I wanted to add strain. So I'm going to go equivalent of Miser's strain. You notice the lightning bolt is there. I can hit solve, but this would run through the whole cycle again, and I'd be sat here for a while. If I right click on where the lightning bolt is, evaluate all results, what it will do is take the present solve that's been completed and give me an update based on that. So what we've got now is a basic bar running, and we have these. So we've now got some sort of results. Let's just look at the stress. Now according to this, it is 2.1666 e to the power of 7 maximum. A lot more to cover on this yet, but let's just say this is our highest. The one thing that you may have been used to is in some softwares it will say that's at the peak of the material that you've selected. This system will not do that, it will just run through. So at 2.166 e to the power of 7, so let's go to the solid, we go to material, we go to aluminium alloy, let's go to edit aluminium alloy. Oh, there we go. So this is into aluminium alloy. So the maximum Young's modulus 7.1 e to the power of 10, and we know our result on this was 2.1 e to the power of 7. Okay, so we've got a stress. Shall we figure out? Let's just try and figure out the factor of safety of what's occurring around here. So first things first, I want to know what the maximum safety factor will be. Based on the maximum safety, the safety factor, sorry, I'm just waffling on. What we're going to do is we're going to divide the material ultimate strength by the working stress load. In this case, let's have a look. Working stress load, we need to round this down because it's somewhere in between here, but we'll go with the maximum. So let's go 2.666 e to the power of 7. Now I've put this in a little bit of an Excel spreadsheet, so I've gone 2.66 e to the power of 7, and then we need to find out what the ultimate working tensile strength is. So I'm going to go right onto solid, I'm going to go to aluminium alloy, and then I'm going to go to, well, I'm not going to edit it, but I'm going to click on edit. That'll be fine, we don't need to edit it, but I just want to see what the ultimate tensile strength is in this case. It's actually 3.1 e to the power of 8. If we run that through and we simply do the ultimate tensile by the working stress, it gives us 1.4 to the power of 1. So it's basically, it's around 14, 15 that we're talking about for the maximum. So let's first have a look. Now what I'm going to do is on my equivalent stress, I'm going to right click, insert, fatigue tool, and then I'm going to right click. If you look on here, you go down, we're looking at stress life, mean stresses. We can do all sorts here. We can look at Goldberg's, the mean stress curves. We can look at all different types, but for this point we'll keep in these basics. I'm going to right click, go insert, and I want to know the safety factor. And like before, I'm going to right click, go evaluate all results. Now we notice here, safety factor in this case is when it's at a solid state, it's at this comes back as 15. Now our initial calculations came back at around 14.3.4. It's because the mesh is so clumsy at the moment, it's going to be quite a large error safe between the two. When the component goes through its overall, we actually get a performance of 3.8. So the maximum is 15 and the minimum is 3.8118. Anything below 1 is a failure and should not be pushed forwards. Depending on what the component is that you're doing, you may end up, so a factor safety of, say, let's say a chair. Let's say you want to make a chair that's going to be very, very safe. So you may make a chair that can withstand the weight of somebody who's 50 stone. Or I should say 1,000 kilos. It's a big chair. But and then what you want to do is you're going to introduce a factor safety of 2. So what we do is divide that and we go 500. So what you do is you design it to 1,000, but you sell it with the capability of 500, and it has a factor safety of 2. It could be doubled for its true performance. This gives you an operational window of how well it will perform in certain states. Now in this loading, this state, this is what you get. So that is the basic overall of getting started with Workbench Static Structural. I'm going to close this. Whoops. And I'm going to just come back to my original data space. Click save if you've not done already. One last thing I wanted to show you, and then we are done. Note some results. Let's say now I wanted to change it. I wanted to add a thermal aspect to it. I wanted to look at modal analysis. I wanted to put it into different states to look at failure under frequency analysis. I'm going to right click on results. Notice here we've got transfer data from, or transfer data new. Wow, it's actually not allowing me to transfer anything. So let me go on solution. Right click data. There we go. Now it's because I clicked on results. It went, well, you just want to send the pictures? I have no idea what you're talking about. So because we've done the FEA on a singularized part, what we could do if we wanted is we then could look at the bar in explicit dynamics. We could look at it moving through space. We could look at it being a projectile or being a fixture of some sort. It would allow us to transfer the present data across. This is why ANSYS is known as one of the biggest multi-physics tools. You actually grab different physics tools within it and you add them together to give you a bigger picture of what's going on. Right, so if you've not done already, hit save. I hope you found this a bit of an easy intro. I hope you found this a nice fluid process. If there is any questions, please do not hesitate. Come and see me, we'll have a chat, and I can help you along with as much as you like. If you've any other questions, again, you can email my normal email address. You can come and see me in the office, CM123, 123 if you forget the number, wow. But yeah, come and see me, we'll have a chat, and yeah, speak to you all soon.